All right, so we covered where a sine wave comes from. Let's take another look at these sine waves that I have drawn here. So again, I have, if this is my x-axis, I could also just make this axis whatever I want it to be, whatever my variable is. And, maybe even phi would be my variable. And I could say, what is the, let's say that my function is a function of phi. And I want to know what the sine of, let's call this f of phi. And let's say I want to know what is the sine of 90 degrees. So I come to my plot, I go to 90 degrees, and I go up, and I can see that the y value here, let's just, we don't know the amplitude or the height of this sine wave, but we know that that would be the max, right? And so when you're in geometry and when you learn this stuff in school, I particularly remember asking myself and asking my teachers and asking other people, what the heck is sine? What is cosine? What do these things even mean? Well, this is what it means. It means the y coordinate of a vector rotating around in a circle, which is exactly what we did here. So if I go to 90 degrees, the y coordinate is at its peak. If I go to 180 degrees, the y coordinate is at a 0, right? So again, here's 180 degrees. The y coordinate is at 0. I go to 270 degrees. The y coordinate of this graph, of this rotating vector, is at a negative maximum, right? Which is here. And if I keep on going, I get back up to this point here where I've now reached 360 degrees. Or I can look at it as 0 degrees again, and my y height here again is 0. There's no height to that point, and I'm back at 0. And then this just keeps on repeating over and over and over. And that is what a sine wave is. So if at any point, so this would be 360 degrees, this would be 720 degrees, and we're just talking about cycles now. This is the same thing happening over and over again. So, this portion of the wave is the exact same as this portion of the wave, except that one happens, later on. And then this one, which also happens later on. And so I'm saying later on, well, what the heck does that mean? I don't have to plot degrees here. I can actually plot something like time, okay? So let's say I do have a vector and I want it to take one rotation per second. It's going to sweep around in a circle. It's going around, and then it's going to complete a rotation in 1 second. Well, if that's the case, I can, swap out time or my degrees here for times. So I could call this 0.25 seconds. And then I could call this a half a second. And I could call this 0.75 seconds. And then one complete rotation would be 1 second. Okay, and so that's exactly what we do in engineering. Typically, we're dealing with these sinusoidal voltages or currents that are changing with respect to time. And how long it takes to make one full cycle is known as the period, or capital T, of the signal. Okay, so in this case, my T was 1 second. And the frequency of a sine wave is equal to 1 over the period, and it basically tells me how many cycles per second. Okay, so if the frequency, or for a 1 second period, would be 1 cycle per second, right? That makes sense. 1 cycle per second. So what if I made my period even smaller? Let's say that I made it, let's actually go on to the next slide. I guess I'm getting a little bit ahead of myself, but that's okay. Let me just explain it now, and then we can explain it again later. Let's say I made my period even shorter, so I complete a cycle in half the time, and so I complete 2 cycles in 1 second. Now my new period would be half the time. It would be half a second, right? So if I want to find my frequency there, I would say it's 1 over a half a second, or 2 right? 1 divided by a half, 2 cycles per second. And you may have seen this before, but this unit, cycles per second, is usually replaced by the unit which we call hertz, which is equivalent to cycles per second, but it's the unit that we use for frequency, okay? So a signal that oscillates at a rate of 1 cycle per second is a 1 hertz signal. A signal that oscillates at 2 cycles per second is a 2 hertz signal, okay? So hertz, again, just means cycles per second, but that is the unit that we use for frequency. Okay, so I'm going to go ahead and stop this video here. Hopefully everything here is clear. Again, the cosine wave is the same exact thing as the sine wave, except instead of tracking the y coordinate, we're tracking the x coordinate of this vector that we have rotating in a circle. I'm typically going to use sine in this class because the LT spice source for AC sources, or sorry, for AC circuits uses the sine. So just to avoid confusion and to keep things simple, I'm typically going to use sine. But we can, later on explore the differences between sine and cosine, and ultimately it doesn't make any difference in terms of the behavior of the circuit. It really just makes a difference in terms of the math, okay? But the circuit will behave the exact same whether I use a sinusoidal source or a cosinusoidal source, assuming everything else about that wave is the same except for the shift in time, okay? Let's go ahead and end this video here before I get too far ahead of myself. I've already gotten a little bit ahead of myself. So if this doesn't make perfect sense yet, don't worry about it. But it is important to note that frequency and period are inverses of one another. It's important to note that the period is the amount of time it takes to complete one cycle. And it is important to note that the unit of frequency is hertz, which is equivalent to cycles per second. Okay, so I'm going to end this video.